As the Ice Age drew to a close, the world was on the cusp of dramatic transformation, and so too were the humans who had roamed it for millennia. By the time of the Younger Dryas, humans had spread far and wide, from the icy tundras of the Americas to the sun-baked plains of Australia, carving out lives across every corner of the earth. This sudden, harsh cold snap posed a new set of challenges for these resilient hunter-gatherers. Far from stalling human progress, the Younger Dryas ignited new strategies, forcing early societies to innovate and adapt. As the world's landscapes shifted, so too did the dynamics of human survival. From the icy reindeer hunts of northern Europe to the strategic fishing in the southern regions, the end of the Ice Age tested human ingenuity like never before. This critical period not only shaped the way humans interacted with their environments, but also paved the way for the rise of agriculture and complex societies that would define the Holocene. The last glacial period, also called the Weichselian in northwest Europe, occurred between 115,000 and 11,700 years ago. It was marked by significant climate changes, with temperatures swinging between cold stadial and warmer interstadial periods. These fluctuations were recorded in ice cores from Greenland and sediments from the North Atlantic Ocean. There were also abrupt, intense cold events, known as Heinrich events, during this time. These shifts in climate impacted animal populations and humans, altering migration routes, causing some species to evolve in isolation, and leading to higher extinction rates during the coldest, driest times. The coldest phase of this period, called the last glacial maximum, happened between 26 and 19,000 years ago. During this time, the Earth's ice sheets were at their largest, sea levels were about 120 meters lower than today, and the global climate was generally colder and drier. Greenhouse gas levels, especially carbon dioxide and methane, were much lower, contributing to the cooling. The drop in temperatures, ranging from 4 to 10 degrees lower than pre-industrial levels, was mainly due to the reduced carbon dioxide and the massive ice sheets. Other factors like dust and vegetation changes also played a role in this cooling. After the end of the last glacial maximum, humanity had successfully colonized most of the Earth's habitable regions, showcasing remarkable adaptability and ingenuity. In Eurasia, dense populations thrived in Europe, Asia, and the Middle East. The Fertile Crescent was on the verge of transformative agricultural developments, with evidence of early plant cultivation and animal domestication. Technological and cultural innovations spread widely, facilitated by trade and interaction. In Europe, the landscape during the last glacial maximum was dominated by tundra and steppe, cold environments where animals like horses, reindeer, and mammoths thrived. Human populations, who had arrived in Europe around 45,000 years ago, were concentrated in areas with more favorable climates, like southwest France and the Iberian Peninsula, where they survived the last glacial maximum in refuges. After the ice began to retreat around 19,000 years ago, humans expanded and gave rise to cultures like the Magdalenian. In South Asia, communities along river systems like the Indus and Ganges thrived, utilizing abundant resources and engaging in early forms of plant and animal management. East Asia saw the development of increasingly complex societies, particularly in regions like the Yellow and Yangtze River valleys, which would later become centers of agricultural innovation. In Southeast Asia, humans adapted to dense forests and coastal environments, relying on fishing, hunting, and foraging. Island populations, such as those in what is now Indonesia and the Philippines, demonstrated early maritime skills, facilitating trade and cultural exchange across the region. In Australia and Oceania, humans had established themselves tens of thousands of years earlier, adapting to unique challenges in arid deserts and coastal ecosystems. In the Americas, Humans had spread widely across North and South America, navigating diverse environments from icy tundras to tropical forests. Distinct cultures emerged, such as the Clovis in North America, and those associated with fishtail points in South America, reflecting advanced tool-making and survival strategies. These early populations utilized both megafauna and smaller game, while adapting to changing climates. Globally, migration patterns during this period were shaped by coastal routes, river valleys, and land bridges like Beringia, which connected Siberia to Alaska. As the Ice Age ended, melting glaciers raised sea levels, altering landscapes and creating new barriers. This period marked the dawn of the Holocene and set the stage for the Neolithic Revolution, ushering in agriculture, permanent settlements, and the rise of complex societies. The Younger Dryas was a sudden cold period that lasted about 12,900 to 11,700 years ago. It interrupted the warming trend at the end of the last ice age, and has been studied more than any other climate event in history. While many theories focus on a dramatic event like a massive flood to explain its origin, some scientists argue that the Younger Dryas was just a natural part of the sequence of events during the transition from glacial to warmer periods. One key feature of the Younger Dryas is that it resembles other cold spells in Earth's history, called Dansgaard-Oeschger events. These events happened during ice ages and were caused by disruptions in the Atlantic Ocean's circulation. During the Younger Dryas, fresh water may have pooled on the ocean's surface, leading to the formation of thick sea ice. But vaster changes in climate meant that fresh water may no longer be obtainable. Most water resources on the planet have been wiped out. This sea ice blocked heat from escaping the ocean, shifted wind patterns, and reflected sunlight away, thereby creating freezing and Siberian-like winters in the North Atlantic region. This cooling affected weather patterns far away, weakening the Asian monsoon and shifting tropical rain belts southward. A popular theory suggests that the Younger Dryas was triggered by a massive release of fresh water from Lake Agassiz, a large glacial lake in North America. This fresh water could have slowed or stopped the ocean currents that normally move warm water north, leading to rapid cooling. Evidence supporting this idea includes a significant drop in the lake's water level and changes in ocean chemistry around the time the Younger Dryas began. However, this theory has faced challenges. Scientists haven't found clear physical evidence of floodwaters flowing from the lake, and the timing of the lake's drainage is uncertain. Some researchers think the cooling might have been caused by a slowdown in ice melting rather than a massive flood. Additionally, ice core records from Greenland show that the start of the Younger Dryas was not as abrupt as other climate shifts, suggesting it might not have been caused by a sudden catastrophe. Interestingly, while the Younger Dryas began with a gradual cooling, its end was extremely fast. Temperatures jumped back to warmer conditions in just 1 to 3 years. This sudden end remains a mystery and highlights how complex and dynamic Earth's climate can be. The Younger Dryas was not an isolated or unusual event, but rather a critical part of the natural sequence that ended the last ice age. Antarctic ice cores reveal that during the deglaciation, warming and rising carbon dioxide levels stalled during a period called the Antarctic Cold Reversal, which lasted from 14,500 to 12,900 years ago. This stalled state needed a major event to restart the climate transition, and the Younger Dryas fulfilled that role. The Younger Dryas shared many similarities with an earlier cold phase known as the Mystery Interval, between 17,500 and 14,500 years ago. Both periods coincided with warming and carbon dioxide releases in Antarctica caused by upwelling in the Southern Ocean. This process brought nutrient-rich, deep sea water to the surface, releasing carbon dioxide into the atmosphere and altering ocean chemistry by mixing older carbon-depleted water with surface waters. Evidence from marine records supports this connection. Sediments show disruptions in ocean circulation, with unusual chemical ratios in the North Atlantic and Central American waters during both the Younger Dryas and the Mystery Interval. These disruptions likely contributed to cooling in the Northern Hemisphere, affecting global climate patterns and slowing the overall warming trend. On land, further evidence links these two events. Cave records in China show weaker monsoon rains during both periods, while normally dry caves in Brazil grew stalagmites, reflecting changes in rainfall. Coastal sediments off Brazil show spikes in river debris, and pollen records in Florida reveal shifts to cooler, drier conditions, with more pine trees. These regional climate changes highlight the global impact of both the Younger Dryas and the Mystery Interval. Unlike smaller, shorter climate shifts like Dansgaard-Oeschger events, the Younger Dryas and the Mystery Interval were part of larger-scale disruptions linked to the end of the Ice Age. This suggests the Younger Dryas was not a random anomaly, but an essential part of the Earth's transition out of glacial conditions. The climate patterns observed during the Younger Dryas are not unique to the last glacial termination. Similar sequences have occurred in previous transitions from glacial to interglacial periods. For example, around 129,000 to 120,000 years ago, during the transition to the Eemian interglacial, there was a brief warming event similar to the Bowling-Allerod phase. The transition that occurred approximately 243,000 to 230,000 years ago, leading to a warmer interglacial period, provides an even clearer example, with equivalence to the Mystery Interval, the Bowling-Allerod warming phase, and the Younger Dryas cold phase. These intervals, spanning several thousand years, illustrate that such cold reversals are recurring features in the deglaciation process. Evidence from Chinese stalagmites and Antarctic ice cores supports this conclusion. Weak Asian monsoon periods during terminations were tied to cold conditions in the North Atlantic, which influenced Southern Ocean warming and carbon dioxide release. These processes contributed significantly to the climate transitions in southern latitudes and the melting of ice sheets in the Northern Hemisphere, reinforcing that such patterns are a natural part of glacial terminations. The data show that weak monsoons and associated cold periods were either prolonged during slow deglaciations or shorter during rapid transitions. These intervals seem to be driven by changes in northern solar insolation and interconnected climatic systems, rather than isolated catastrophic events. For instance, Heinrich events involving massive discharges of icebergs acted as periodic drivers for these transitions, but were not sole determinants of the Younger Dryas. While some argue that a one-time catastrophic event, such as a flood or extraterrestrial impact, might have triggered the Younger Dryas, this view is unnecessary when considering the broader context of the last four terminations. The Younger Dryas caused significant changes in plants and animals, especially in the Northern Hemisphere. This has led researchers to question whether human populations also declined or reorganized during this time. Some studies suggest that the Younger Dryas may have led to changes in population size, how humans used resources like stone for tools, and patterns of human activity. Climate shifts, like the Younger Dryas, can greatly impact ecosystems and human societies. For early humans, these changes could have affected food availability, possibly leading to population bottlenecks, conflicts, or even disease outbreaks. An example of a similar but smaller scale event is the Little Ice Age, 1300 to 1800, which caused crop failures and social unrest in some areas. However, during the Younger Dryas, humans were still hunter-gatherers and not yet farming or living in complex societies, making their responses to climate changes different. Studying the Younger Dryas helps us understand how early humans adapted to major climate changes, which is essential for understanding human history and the impact of future climate changes. The Younger Dryas played a pivotal role in the development of agriculture in Southwest Asia, particularly in the Levant. During this time, the environment became harsher, disrupting the established patterns of life for human groups, who had previously thrived during the warmer and wetter late glacial period. This environmental stress acted as a significant catalyst for the transition from a hunter-gatherer lifestyle to an agricultural one. As the climate turned drier, the vast forests and open forest steppe zones that hunter-gatherers relied on shrank, reducing access to the abundant plant and animal resources. In places like Abu Huraira, there is evidence that people adapted by modifying their plant-gathering techniques in response to these changes. While hunting, especially of species like the Persian gazelle, remained relatively stable, the availability of wild plants began to dwindle, which put pressure on people to find new sources of food. This stress likely prompted the experimentation with domesticating plants and animals, setting the stage for agriculture. Furthermore, the cultural impact of the Younger Dryas cannot be overstated. In areas like the Natufian heartland, larger, more sedentary settlements with advanced tools were abandoned as environmental conditions worsened. As food became scarcer and more difficult to obtain in the traditional ways, people had to adapt by becoming more mobile, resembling lifestyles from earlier, harsher periods. This mobility was likely a response to the diminishing wild resources, driving the need to explore and experiment with new forms of subsistence, such as cultivation. While the Younger Dryas itself may not have been the sole cause of the shift to agriculture, it certainly acted as a powerful trigger. The climatic deterioration forced groups to rethink their subsistence strategies, particularly in the face of shrinking wild resources. In combination with other factors, such as population growth and the increasing trend toward sedentary life, the challenges posed by the Younger Dryas pushed societies toward farming as a more reliable and sustainable way to meet their food needs. Thus, the Younger Dryas played a crucial role in promoting the development of agriculture. The environmental stress it caused, particularly the scarcity of wild plant and animal resources, acted as a catalyst that led human groups in the Levant to seek out new, innovative solutions to feed growing populations. This transition to farming marked a key moment in human history, setting the foundation for the agricultural societies that would shape the future of the region. During the Younger Dryas, human populations across North America experienced a significant drop, or major changes in how and where they lived. This cooling period disrupted earlier warming trends, leading to challenges for the people living during that time. Evidence suggests that many communities shrank in size, moved to different areas, or adopted new ways of surviving in response to the colder climate. In North America, spear points used for hunting reveal how people adapted during this period. Before the Younger Dryas, people used a tool type known as Clovis points. As the climate cooled, these tools were replaced by more advanced designs like Folsom and Redstone points. Over time, simpler tools replaced these, reflecting how people adapted to changing conditions. However, the number of tools and evidence of human activity during this time dropped sharply, suggesting fewer people or significant changes in their way of life. In some regions, like the southeastern United States, the decline in population or activity was particularly steep, with fewer tools found at important stone quarries that had been heavily used before. This suggests that either fewer people lived in these areas or they relied less on these sites during the Younger Dryas. In Alaska, there was an even more dramatic shift. Evidence of human activity completely vanished for about 200 years at the start of this period. Interestingly, after several hundred years, populations began to recover even though the climate remained cold. This shows that people found new ways to adapt, such as moving to more favorable areas, changing their survival strategies, or forming new communities. In other parts of the world, similar patterns were observed, but not everywhere was affected the same way. For example, the Middle East saw its population grow during this time, possibly serving as a refuge for people fleeing harsher climates. Later, around 9,000 years ago, during another period of climate change called the Altithermal, populations declined again, but the reasons for this drop are less clear. Despite these challenges, human populations eventually recovered, showing their ability to adapt to changing climates and environments. During the late glacial warming, humans began returning to northern Central and Northern Europe, regions that had been abandoned during the Ice Age. Radiocarbon dating shows that resettlement started early in this warming period, and people lived in or returned to these areas repeatedly. As the climate warmed, forests grew in northern Europe, allowing hunter-gatherers to spread into areas like southern Scandinavia, where they adapted to forested environments. These early humans used small, portable shelters and stone tools such as arrowheads and scrapers. They hunted various animals, including red deer in the south and moose in the north. Unlike earlier cultures, they produced fewer bone tools and artwork. Their ability to adapt to changing environments with new tools and strategies helped them survive in different landscapes. Around 11,000 years BC, the eruption of the Glacial volcano in central Germany spread volcanic ash across Central Europe. The eruption had little long-term impact, and hunter-gatherers quickly returned to the region, continuing their way of life. Archaeological evidence from these sites shows that their tools and hunting methods remained the same. During the late glacial warming, two groups of hunter-gatherers emerged, one in the south using smaller tools, and another in the north using larger, specialized tools suited for cold, open landscapes. This distinction highlights how people adapted differently to changing climates. The Younger Dryas, which followed the warming period, caused dramatic climate shifts. Some areas became colder again, with permafrost conditions reappearing in the north, while southern areas stayed milder. The eruption of the Katla volcano in Iceland added to the environmental changes, causing erosion in some areas. These climatic shifts affected both wildlife and human activity. In the north, reindeer were hunted with specialized tools, while in the south, red deer were still the main food source. People continued to adapt by developing new tools, such as fishing hooks and early bows and arrows, to cope with the changing environment. During the Younger Dryas, humans across Europe displayed remarkable resilience and adaptability to harsh climatic conditions. They developed specialized tools such as stone points, scrapers, fishing hooks, and even boats to exploit diverse resources effectively. In Europe, the Ahrensburgian culture, a prehistoric group, lived during the Younger Dryas around 12,000 to 10,000 years ago. This culture is known for its distinctive tools, such as tonged points, and its reliance on hunting large mammals like reindeer. The Ahrensburgian groups are believed to have been highly skilled in seasonal hunting, relying on migratory herds of reindeer that traveled between winter and summer grounds. These groups likely used tools made from reindeer antlers, such as axes, and may have hunted in collaboration with dogs, which helped with hunting and transportation. The Ahrensburgian people's mobility and resourcefulness allowed them to adapt to the harsh climate of the Younger Dryas. Strategic hunting practices like reindeer drives at Stellmore and Schleswig-Holstein and the use of aquatic resources, evidenced by reindeer antler boat fragments, highlight their ingenuity. Communities maximize natural materials, creating tools, jewelry, and symbolic artifacts, like the drilled molar necklace from Remouchamps in Belgium. Archaeological evidence, such as the systematic processing of reindeer carcasses and diverse tool assemblages from sites like Kartstein, Stellmore, and Alt-Duvenstedt, underscores their resourcefulness in enduring long winters and adapting to varied landscapes. These innovations not only ensured survival, but also laid the foundation for future cultural and technological advancements amidst environmental challenges. During the Younger Dryas, there was a possible population decline in Japan. However, pottery use, which began earlier, persisted and resurged in the Holocene, reflecting continuity in social networks and resource use. Hunter-gatherers adapted to environmental changes by shifting to more specialized foraging, exploiting aquatic life and plants, and gradually moving toward sedentary lifestyles, as evidenced by the emergence of shell middens and increased pottery reliance. Younger Dryas was a pivotal period marked by significant climate disruptions that shaped both natural ecosystems and human societies. As one of the most studied climate events, it exemplifies Earth's dynamic climate transitions during glacial terminations. Its global impacts, such as altered ocean circulation, weakened monsoons, and shifts in vegetation, triggered profound adaptations in human behavior. Early hunter-gatherers displayed remarkable resilience, developing new tools, strategies, and social structures to cope with harsh conditions. This period also acted as a catalyst for transformative changes, including the advent of agriculture in the Levant and increased cultural exchange in Europe. The Younger Dryas underscores the interplay between climatic shifts and human ingenuity, offering critical insights into how early societies navigated environmental challenges.